Hi, Robin Beaumont here. Welcome to the fourth tutorial looking at p-values. This time I'm making some use of an excellent material produced by Cumming, who has also just produced a good stats book called Understanding the New Statistics, published by Routledge. If you buy only one stats book this year, make it that one. So far we have considered probability and sampling aspects of p-values, as well as seeing how, because the p-value is just another statistic, it also varies across random samples, which people tend to forget. In this session we are concentrating on how we can combine certain rules alongside the p-value to make logical decisions, and what the p-value distributions are for these alternatives. But first, a 10-second review of where we're up to with the p-values. So far we have looked at the probability aspects of the p-value. That is, a p-value is a conditional probability which considers a range of outcomes for the particular statistic we calculated. It is equivalent to a specific area in the probability density function. We also looked at the variability of the mean across samples and discovered that the standard error of the mean is simply the standard deviation at the across sample level, and in fact allowed us to predict the accuracy of our mean estimate from a single sample to an infinite number of samples. In the last session we discovered that the p-values differ from one random sample to another when taken from the same population. We noted that it did not follow a normal distribution. In fact, using a computer simulation, mimicking the situation of the null hypothesis actually being true, we demonstrated that they were equally likely from 0 to 1, and such a situation is modelled by a uniform distribution, you will remember. We used Cumming's excellent Excel simulation to see how this actually worked out with his dance of the p-values, and we also recommended looking at his YouTube video. The common theme of all the above is that we have assumed that the null hypothesis is true, but clearly in reality this is not always the case, and this is what we're going to consider in this session. So, a rule simply tells us how to behave, and often rules are for the general good and not necessarily for the individual or for a specific situation. Remember what I just said, as it will come in useful later, I promise you. Here is a result from the amylase experiment from the previous session with a p-value of 0.0188. As you know, we can say, given that the sample of 15 was obtained from a population with a mean of 120, a t-statistic of minus 2.656 or 2.656, or one more extreme, will occur 1.8% of the time. We can note that this p-value is less than 1 in 20, that is 0.05, and we can mark this 1 in 20 t-value or equivalent p-value on the PDF diagram. There. These marks represent what are called critical values. Obviously we can set the critical values to be anywhere we want. The area more extreme than the critical value is also given various names, for example the critical region. Clearly this region has an area, and in this instance we know it's 0.05, which is the same as the p-value threshold we set. And as you know, p-values are just areas under the curve, so we'd expect this to be the case. The critical region is also called the alpha level, and we say here we've set the alpha level to 0.05. Because in this example we have two identical regions in the tails, each critical region is equal to alpha divided by 2. Now let us create this rule which says that if our p-value is more extreme than our level of acceptability, that is our critical value, we will reject the parameter value we based the p-value on. This is simply often stated as we reject the null hypothesis, but what we're talking about really are parameter values. The important thing to note is that we are rejecting the premise on which the p-value was calculated, and more about that later, and it is not really that simple once you start getting into it, as we will see. By making this decision, we are dismissing the possibility that our sample came from a population mean of 120, even though we know that we can get such a t-value rarely. Hence the alpha value is also called the type 1 error. Let's review what we have done. We developed a rule which simply told us how to behave in a certain way. We set a level of acceptability, which we called critical value. We decided here upon the 1 in 20 level, but obviously we could set it at any level. Common ones are the 1 in 100 and 1 in 1000 levels. When the p-value is anywhere within this critical region, we reject the parameter value we base the p-value on. This is often simply stated as we reject the null hypothesis. The important thing to note is that we are rejecting the premise on which the p-value was calculated, and more about that later. Also note that it does not matter how far inside or outside the critical region the p-value is. In our amylase data example, this means because our p-value was less than the critical value, we reject the possibility that our sample came from a population with a mean of 120. We can state this question in a more general way. When we have rejected one particular parameter value we based our p-value on, what value should we replace it with? Unfortunately, the suggested solutions made by various statisticians to this problem has resulted in nothing short of a war. But first let's consider why we want to set this arbitrary level so that we can reject this parameter value. So why might we want to reject the null distribution? Well, first it enables decision making. That is, it moves things forward. For example, if the sample did not come from the null distribution, it indicates it came from another. And as the null distribution of the nil effect, accepting any alternative one means there must be some sort of effect. Let's reinterpret our amylase data in this manner. Say we know that in a population the mean value of substance X here is 120, and we know that this high level of substance X indicates that people have a propensity for a range of nasty diseases. Just think cholesterol and diastolic blood pressure here. We give 15 random volunteers a medical drug Y, think statins and Benecol here, which we believe reduces the level of nasty substance X. If the probability of obtaining our t-value and its associated p-value is below a certain critical threshold, we can say that our sample does not come from the null distribution, and therefore the medical drug has had some type of effect. Now let's get back to the alternative distributions, which will also help us consider what we mean by effect. 100 Years' War did what it said, that is, it went on for 100 years, which is about the length of time discussions have been going on about the nature of the alternative distribution. This time the war is basically between three factions. Sir Ronald Elmer Fisher, who lived from 1890 to 1962, is rightfully considered to have been the greatest 20th century statistician to ever have lived. He believed that by rejecting the parameter value we used for the basis of our p-value, all we could do was accept that there was an infinite number of alternatives. We can express this simply by saying, in this instance, considering our amylase/miracle drug data, that the population parameter value of a mean of 120 is the null hypothesis versus the infinite number of alternative hypotheses where the population mean does not equal 120. From our PDF graph of our amylase/miracle drug data, we know we can express this also as t-values. That is, our null hypothesis is that t-value which is equal to 0 versus the alternative hypothesis that it is not equal to 0. In the 1930s along came two Bolshevik Americans to upset this quintessential Englishman and suggest that it is more useful in the long run to specify a clear alternative hypothesis. Neyman Pearson, and to a lesser extent Gosling, Acker student, who also developed the t-test, proposed a specific second distribution. So now we have still the population parameter value of a mean of 120 for the null hypothesis, but this time a specific parameter value for the alternative hypothesis, which I've called XXX here. We'll see what this value is for amylase/miracle drug data shortly. There is a third group in this war, a group known as the Bayesians, who suggest that basically the researcher uses knowledge of the subject area which they set the conditional parameter value in the p-value. In recent years they have gained ground, and we will look quickly at this approach as well in the next session. The war is still going on to a certain extent, the main problem being that many elementary statistics books muddle all three approaches together, making the whole thing totally illogical. You may have noticed that so far I have always interpreted the p-value by only considering the null hypothesis, but now we will consider the alternative hypothesis as well. Here we have the null hypothesis distribution, that is t equals 0 for amylase/chemical drug data in blue, and something creeping up on the right hand side. This red distribution is the alternative distribution, but notice that it is moving. This is how Fisher perceived it. While the nil hypothesis is stable, in other words fixed, there are an infinite number of alternative hypotheses. Notice how the red ones, that is the alternative distributions, change shape as they move away and closer to the null distribution. Three things to note. Their peak reduces in height, therefore becoming flatter, and also they become more asymmetrical, leaning towards the null distribution, and like the flatness, this becomes more prominent as the distribution gets further away from the null distribution. However, when the alternative distribution is equal to the null distribution, that is when they coincide, both were identical. A logical question follows from this idea of the alternative hypothesis distribution. How did we define it? Well, it is remarkably easy, because both the null hypothesis distribution and any alternative distribution, when we are talking about t-distributions, actually comes from the same set of distributions. It just so happens that for the null hypothesis distribution, the parameter value is equal to 0, and for any specific alternative hypothesis, it is equal to a specific value. This value, which is just another parameter value of the t-distribution, has a terribly off-putting name, the non-centrality parameter. It always sounds to me a bit like a psychotic illness. So all this time, where you have been specifying t-distributions, you have been assuming that the null centrality parameter is equal to 0, and therefore not considered it. The non-centrality parameter can be thought of as a type of effect size, which we'll look at a bit more now to get us to understand the alternative Neyman Pearson approach with the specific alternative hypothesis. So, in the Neyman Pearson approach, we have a specific alternative, and it is the t-distribution around the mean of a sample in the miracle/amylase drug example. So we know the null distribution is around t equals 0, and now we have the alternative distribution around t, which equals minus 2.656. This is the value we obtained when we worked out the t-value of our sample. So now we have the distance between the two distributions, and this distance is called the effect size. The effect size can be measured in several different ways, one of the most common being Cohen's d. Cohen's d is simply the difference in the means divided by the standard deviation, like the z-score you may remember. From our results, we have a value of minus 0.6857, and this tells us that the difference between the mean of the population and their sample is just over 2/3 of a standard deviation. We could also consider the t-value itself, which we've done in the past as an effect size measure. Another measure is the actual non-centrality parameter itself, called delta. The Greek letter capital delta is represented by what looks like a triangle. This is actually just a Greek letter. Delta, that is, the non-centrality parameter in this situation, is simply Cohen's d multiplied by the square root of the sample size. And from the previous slide, I said that this non-centrality parameter is a thing that defines position along the x-axis of the t-distribution. So now, by accepting the Neyman Pearson approach, we have two distinct parameter values along with their distributions, as well as a critical value. Let's look at all this complexity in detail. A marvellous free program called G-Power works out the effect size measures we discussed in the previous slide for us. For example, by simply entering the population mean, standard deviation and sample size, it calculates Cohen's d and also the non-centrality parameter and the critical t-value for a given critical value. Notice here we have selected a critical region equal to 5%, which gave a t-value of 2.144, which you may remember we obtained by hand earlier. As before, the red line is the null distribution, and the red areas represent the critical regions. The blue line is specific alternative distribution, and the blue shaded areas are called the beta regions. While we can only see one, the large one in the diagram in the middle, there's also a very small one between t equals 2 to 3. It's on the far right. But now let's look at each of these regions in a little more detail. First we have the vertical lines representing the critical values. Then the mean of 120 for the null distribution and the mean of 96 for the alternative distribution. We have the two critical regions in red for the null distribution, which indicates where we reject the null distribution for the alternative. We can make two correct decisions, that is, we can either accept the null distribution when in fact it is true, that is the right hand green section, or we can accept the alternative distribution when in fact that is true, represented here by the left hand green section. Notice that the decision we make is dependent upon where we place a critical value, which we are in control of. We can also make two incorrect decisions. Firstly, by setting a critical value, we are allowing ourselves the possibility of making the incorrect decision of rejecting the null distribution when in fact it is actually true. Secondly, we also have a similar region in the alternative distribution, which is where we reject the specific alternative hypothesis when in actual fact it is true. So we end up with four possibilities, which results in two errors and two correct decisions. Often people think that a result from a single experiment can be in both distributions, but this is not the case. It is really important you realise that for a single experiment we have a single result which can only belong to one of the two distributions, but never both. It probably would have been better to have shown the distributions on two separate x-axes. Then you could have thought of the result dropping into one of the curves each time. We have no way of knowing which curve each individual result will drop into. That's the important thing to realise. What we have done in the Neyman Pearson approach is to set up a decision rule which hopefully minimises the possibility of making various mistakes. That is, rejecting a null distribution when in fact it is true, which if we did would be called the first or alpha error, and also the possibility of accepting a specific alternative hypothesis when in reality the null distribution is true, which is called the second or beta error. The Neyman Pearson approach aims to both maximise the possibility of making the correct decisions and minimise chances of making the wrong ones. By considering the alternative distribution a little more, we'll see how we can minimise these errors. Here I've highlighted the two correct decisions, but highlighted in yellow the correct decision of accepting the specific alternative hypothesis when in fact it is true. This yellow area is called the power of the experiment, and when you hear people talk about ensuring an experiment has enough power, this is what they are talking about. The aim is to maximise this yellow area. This yellow area, that is the power, is the probability of obtaining a specific statistic value equal to or one more extreme than the critical value, given that a specific alternative hypothesis is true. As with our usual p-value, it is not telling us if the alternative hypothesis is true, and once again it is a conditional probability, but this time the conditional part of it is the parameter value being equal to that of the sample estimate. I ringed around what this value is in this example. You can see it is 0.69. That is, 69% of the probability distribution lies beyond the critical value. That is, if a result does come from the specific alternative distribution, we have a 69% chance of it being in the yellow area, where we make the correct decision. Ideally, we would like to have a 100% chance of our t-value falling in the yellow region, if it belongs to the specific alternative distribution, but this is practically impossible. And we usually aim for an experimental design which has a power of around 80 to 90% at an alpha level of 0.05. But we will see in a second that usually we should really be aiming for 90% power, which is very rare now at the moment. The next question is, how do we ensure that our experiment can have this degree of power at the planning stage? So let's move on. Well, we again use G-power to provide us with sets of results, this time telling us that the projected power is for various sample sizes for a given effect size and critical value, that is the alpha level. We can say that given the stated effect size and critical value, we can have a situation where we have an insufficient sample size, which will result in us rarely getting a p-value in the critical region. At the other extreme, given the stated effect size and critical value, we can have the situation where we have a sample size that is too large, resulting in us getting p-values that are in critical region always, but the effect size might be trivial. You may wonder why we do not need to specify the variability of the results, that is standard deviation. This is because it is done through specifying the effect size, which is itself partially based upon the sampling distribution of the statistic, which in this instance is the sampling error of the mean. For the last few slides you will have realized that by specifying a precise alternative we have introduced a lot of additional complexities such as effect sizes, non-centrality parameters and power, but this added complexity has given us the added value of being able to make informed decisions and plan experiments that give us a chance of obtaining useful information, by which I mean a p-value in the critical region. I would like to end this session by taking a quick look at the replication of p-values when we know for sure the population from which the sample came is not the null distribution, by once again using results of computer simulations. Here is a very important graph taken from the Cumming 2008 paper, and it shows the distribution of p-values for different situations. Firstly, when the null hypothesis is known to be true, we have equal chances of getting any p-value from a single experiment. In other words, it is a uniform distribution. When we have a Cohen's d effect size of 0.2, that is, the difference between the groups is 1/5 of a standard deviation, we see the curve rise slightly towards the 0 value, indicating that we are more likely to obtain smaller p-values. However, don't get too excited, because from the table we can see that we only have a power of 0.13, indicating that a mere 13% of the area under the curve is to the left of 0.05. Why we chose 0.05 is because that's what we set our alpha level at. This is also equivalent to looking at the 3 bars for the treble, double and single stars. Considering an effect size which is equal to Cohen's 0.5, that is half a standard deviation, which is incidentally slightly lower than our 0.68 that we had for amylase/miracle drug data, we see we now have a projected power of 0.52, indicating now that 52% of the area under the curve is to the left of 0.05. This is an interesting value. It is roughly equivalent to chances of landing heads when you toss a coin. So memorize this. A projected power of 0.5 means that you have as much chance of getting a p-value of less than 0.05 than you have of a coin landing heads. Finally, we have an effect size of 0.8. That is 4/5 of a standard deviation between them. This is slightly higher than we had in our data, but the good news is that now we have just under 90% of the p-values being less than 0.05. In other words, we now have a 1 in 10 chance of incorrectly accepting the null distribution when we have power close to 90%. There are 4 other things to note from that diagram we had on the previous slide. Notice how the power level and Cohen's effect size measure reflected one another. They both went up and both had similar values. Notice how the distribution of the p-value does provide a measure of evidence for the specific alternative hypothesis, and you could say it becomes more accurate as power increases. All the above information is based on computer simulations where we know the nature of the population from which the samples came. In reality, we rarely know that. That is the reason we are doing the experiment. Another difference is that computer simulations allow us to repeat these virtual experiments many thousands of times, but in reality we often rely on a single experiment. Replication is a vitally important research strategy along with the statistical analysis and meta-analysis. An alternative strategy for a single experiment is to make sure the design stage includes a power analysis, and your report focuses on confidence intervals and effect size measures as well as p-values. Finally, when you are specifying the null and alternative hypothesis in your research design, always state the specific alternative hypothesis rather than a nebulous Fisherian one. We have worked through a lot of material in this session, and there is much more material along with exercise in my website. That is www.robin-beaumont.co.uk/virtualclassroom/contents.html. I have presented a rather simplistic view of the differences between Fisher's and Neyman Pearson's approach, and I think I've been rather hard on Fisher. He developed a concept called likelihood, which is very interesting and very useful. Also, do not forget Cummings' book called The New Statistics. In the next section we will look at the advantages and disadvantages of using various alternatives and enhancements to the p-values. Bye.